Welcome to lesson 4. We're almost done with lessons that are diving deeper into topics that we've already covered. There will be one more where we continue looking at sinusoidal and trigonometric functions a little more deeply. And then we're going to move on to kind of the beginning topics of calculus, which is going to be really interesting and exciting, and we're going to learn some of the key concepts that are going to allow us to discover some really fascinating facts about functions. So in this video, we're going to look at the definition of radians again, the unit circle. I'm going to talk more deeply about the special right triangles that we kind of brushed over in Algebra 2, and I'll give you the proof for why those work out the way they do. And then we're going to look at secant, cosecant, and cotangent, which are just reciprocal functions. So if you remember the reciprocal, what that means, you should be in good shape. And then the Pythagorean identity, which sounds very similar to something you know very, very well and is very similar. So all this stuff will be playing off of things you already know and should be a lot of fun. Okay, so you may or may not remember the definition of radian measure, but it's pretty simple. An angle is, you can construct an angle by starting with your initial side and then rotating a certain length around your circle to a point where you stop, and that gives you your terminal side, and that's your angle. And one way of defining an angle is with radian measure as opposed to degree measure, and the way that we define it is by looking at the arc length that you have to travel in order to create this angle and dividing it by the radius. And so the angle measure theta here would be equal to 18 over 4, which is 4.5 radians. Alright, so the radian measure theta of a central angle of a circle is defined as the ratio between the length of the arc, the angle subtends, S, and the radius of the circle, R. Okay, so a lot of words in there, and I want to flesh it out for us. So for any circle, we can create an angle by taking an initial side, rotating a certain length around the circle to a point where we stop, defining that as the terminal side, and that is the angle that we've rotated. And the way that we measure it is in radians, and the way that we measure it is by saying, okay, how far did you travel relative to the radius that you have in your circle? And so in order to define this angle, we'll take the value of S, the arc length, and divide it by the value of R. So to calculate the angle theta, you will take the value of S and divide it by the value of R, the radius. Okay, now there are a couple of terms in here that you may want to make sure you are very clear on. The first is ratio, right? The ratio between two things. This means division, right? So this is why we have division. We're looking at the ratio between two things, right? Division helps us look at the relationship between a quantity and some other quantity. And in this case, it helps us kind of think about how many radius lengths are in the arc length, right? So if I have the arc length S, how many radius lengths are in it? That is the ratio. Then we have the length of the arc, the angle subtends, and this word subtends often gets people. It literally means, and you might want to write this down, the word subtends literally means to be opposite to. Okay? So I'm just going to use the word opposite to help remember what this means. So if I kind of replace that with the idea of being opposite to, the length of the arc opposite to the angle, well, if this is my angle here, from this line to this line, the arc length opposite this angle is going to be this arc length here that was created by rotating around the circle. Okay, so that's the value of S, and of course the radius of the circle, R. Okay. So to put this in words, the angle measure in radians can be found by taking the length of the subtended arc divided by the length of the radius of your circle. And so you can think about how the length of the arc will dictate the type of angle, right? The bigger your arc is, the bigger your angle is going to be, right? Because if you have some circle with a set radius, the more you rotate around it, right, the bigger or wider of an angle you're going to create. So that should make sense. The next big consequence is that an angle does not depend on the size of the circle. So an angle of 2 radians is always going to be the same percentage or portion of the circle. It doesn't matter how big or how small your circle is. And the easiest way to see that is imagine extending both the terminal and the initial rays of your angle that we've created here and draw this arc length. Right? So notice that now your radius is bigger and your arc length is also bigger. And the relationship between the two is going to be the same as it was for this smaller circle here, right? Because we have this same angle being represented by 2 different circles. And so it doesn't matter how big your circle is, right? All that matters is that you're able to compute the radian measure by looking at the arc length and the radius. And so if we can choose any circle we want to, we should pick the circle that is going to be easiest to work with. And that circle is, of course, a circle with radius 1, right? Where the center of the circle is at the origin, or 0, 0. The point on the x-axis is 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And so now we're going to look at a unit circle. And a pretty interesting thing arrives out of the unit circle when we think about the radian measure. And here I've drawn a unit circle. Notice where the radius is now 1. And let's say now that we're going to use this unit circle always to compute the radian measure of our angle. And so the angle theta is, again, the ratio between the length of the arc that subtends this angle and the radius, which in this case is now 1. And so the angle theta is going to be equal to the arc length, S, divided by the radius. But we know the radius now. The radius is 1. And so the arc length is being divided by 1, and anything divided by 1 is itself. And so the angle theta is simply equal to the arc length. Okay? And this is very key and important, and I've talked about this many times, is that an angle in radian measure is referring to the length of the arc that you've traveled around your unit circle. And this is why it is, right? Because the ratio between the arc length and the number 1, well, that's just the value of S, right? If you divide anything by 1, you're just going to get that value. And so what we often refer to as radian measure of an angle is just the arc length around a unit circle that you would have to travel in order to create that angle. So here we have that written out. When working with a unit circle, the radian measure of the angle is equal to the length of the arc. And that's something that we're just going to kind of always commit to memory and have in the back of our heads whenever we're working with radian measures. And so this leads us to thinking about circles more in general and thinking about how can we classify the length of an arc or a 360-degree turn that travels all the way around a circle. And what we notice from that is, look, the circumference of a circle, or the arc length all the way around a circle, is 2 pi times the radius. Well, the radius is 1, so the length all the way around the unit circle is just 2 pi. And so if the length around the unit circle is 2 pi, then the angle, which is exactly equal to the arc length, is going to be 2 pi radians. Okay, and so that leads us to defining a full 360-degree turn as 2 pi radians, and then we can split them up into smaller sections. So a half turn, or 180-degree angle, will be half of 2 pi, or pi radians. A fourth of a way around the circle will be half of that, or pi over 2 radians. Half of that will be pi over 4 radians. And you could also split it up into 30-degree angles. So if you had a 90-degree angle, pi over 2 radians, you could split it up into 3 equal pieces, which would be pi over 6, and so you'd have a 30 degree, a 60 degree, and a 90 degree angle. And those are the angles that we are used to seeing in our unit circle. That doesn't mean that other angles don't exist, but those are the ones that we can kind of wrap our heads around, because they create some very special right triangles that we can use to then find the coordinate points of all the special angles around our unit circle. And we can use that to sort of map out, okay, what will the x coordinate look like as I move around my unit circle? In other words, the cosine. What will the y coordinate look like as I move around the unit circle? In other words, sine. I can think about the slope of the terminal side of my angle as I rotate around the unit circle, and that is referred to, of course, as the tangent of an angle. And there are some other relationships that we're also going to look at. But the great thing about these different functions that we've created by looking at the x and y coordinate and mapping it around the circle is that these create what we know as periodic functions, right? Functions that repeat themselves over time. Because if you think about, the x coordinate at this point here, it's going to repeat itself again over here, right? It's going to be the opposite over here. And so that will allow us to model some real world phenomenon that repeat themselves. And this can be very, very helpful. And in calculus, we're going to look a lot at trigonometric functions because they can be very, very useful. Okay, at this point, we did a lot of review on radians, which is important because it's something that a lot of people don't remember well as they move on in their math career. And at this point, you should feel pretty comfortable with the unit circle. If you don't, go back and watch in the Algebra 2 playlist Unit 6.02 through Unit 6.04. And honestly, all of the Unit 6 videos would be very helpful, but these are the ones where we go into great detail explaining the definition of cosine, sine, tangent, and actually constructing the unit circle. And what I'm going to do right now is actually prove why the special right triangles have the different side lengths that they do, which lead us to the ability to find the x and y coordinates, or the sine and cosine of the angles, the special angles, pi over 6, pi over 4, pi over 3, and then are able to reflect those. So go back and re-watch some of those videos if you feel like you need a little refresher. If not, let's go ahead and talk about these special right triangles. Okay, so let's start with an angle of pi over 6. And you can also think of that as a 30-degree angle, but I'm going to use radians here almost exclusively in my diagrams. And I want to find, as we talked about previously, our motivation is to actually be able to model the x and y coordinates. In other words, the cosine and sine for these different angles as we rotate around our unit circle. And notice, if the cosine is the x-coordinate of this point, well, the x-coordinate of this point corresponds to the x distance traveled in order to reach this point. And so we can label as such right there, right? That is the cosine, or the x-coordinate of that point. And I'll just label it as cosine. And the sine, the y-coordinate, is the distance traveled in the y direction to reach this point. And I can label it as such, sine. And so what we see is that we've constructed a right triangle, right? This line, this y length is perfectly parallel to the y-axis, and this cosine, the x-coordinate, is perfectly parallel to the x-coordinate. And so we've created a right triangle where one of the angles is pi over 6 radians, the other angle is 90, and then if you think about it, this angle here, if this is 90, this is 30, this has got to be 60, or pi over 3. And so what we're going to do is we're going to look at, if we know that the radius of this circle is 1, meaning we know the hypotenuse has a length of 1, what might these other two side lengths be? Okay, so what I've done is I pulled this triangle out over here to the left, and remember, the angle that we're concerned about, this is a pi over 6 angle. we've created a right angle here with my y and x distance. And so that means that I have 90 here, or pi over 2. And then this angle here has to be pi over 3, right? 30, 60, 90, because the interior angles must add up to 180. Now, the value of the green side, right, that's the y coordinate, that's the sine. And what I'm just going to do is use the variable y to represent that, so I don't have to write sine over and over again. And cosine, or the purple side, right, the purple side length is the x coordinate. And so we are going to represent the purple side length as x. And so as we can see here in our diagram, right, the x coordinate of this point is exactly the length of this side, defined as the cosine of this angle pi over 6, and this y value, also known as the sine, that's what it's defined as, is the length of this green side. And just in general, knowing how to prove things that come up as common as special right triangles do is always good, because you never know when a tricky question on a test, even in calculus, will rely on your ability to understand some very simple things from earlier math classes. Okay, so in order to prove x and y, I'm going to take advantage of the Pythagorean theorem. Okay, and I'm also going to take advantage of a special property about equilateral triangles. Okay, so notice here that I don't have an equilateral triangle, right? It is pretty clear that the side length y is going to be smaller than the side length x, and the reason is that the angle pi over 3 is bigger than the angle pi over 6. So this side length has to be bigger because its angle is bigger. Its opposite angle is bigger. But what I'm going to do is I'm going to copy this triangle and I'm going to reflect it over the side length x. Just like that. And so now let's take note of the angles here. So for my new triangle, this triangle that I just copied and reflected over, this angle here is the same as the upper angle right here in our original triangle. So this is also pi over 6. This angle out here is also pi over 3. And this is another right triangle. Okay. And of course the side length here is 1. Alright. Now, what we need to notice is that this of my bigger triangle, so I have now constructed a bigger triangle as well. Okay, so consider this bigger triangle. And in this bigger triangle, this side length is 1, this side length is 1, and right now all we know is that this long side length is made up of two equal pieces that we've called y. Okay, so this big side length is 2y, right? 2 times y. Okay? Let me make that clear. All right, this big side length is 2y. Now, notice that this angle here is a combination, it's an addition of this angle pi over 6 and this other angle pi over 6, both of which, right, 30-degree angles. So if you add two 30-degree angles, or you add pi over 6 plus pi over 6, you're going to get a 60-degree angle, or pi over 3. So this whole angle here, considered as one angle, is pi over 3 radians. Well, now check this out. We have an equilateral triangle. We have all three of the angles being equal, which means all three of the side lengths have to be equal. So this side, and this side of my bigger equilateral triangle have to be equal, meaning that this side length here has to be equal to 1. In other words, 2y must be equal to 1. Well, what does that mean about each side length y? Each side length y must be 1/2. Okay. So now we found the side length of y. And if I come back to my original triangle here, now that I know that y is 1/2, I know the hypotenuse is 1, I can find x by using the Pythagorean theorem, because this side length squared plus this side length squared must equal the hypotenuse squared. And so I'll label this appropriately. Y is 1/2. I'm squaring it. then I'm adding the value of x squared, and that's got to equal 1 squared, which is of course 1. 1/2 squared is 1/4 plus x squared equals 1. And then by subtracting 1/4 from both sides, I get that x squared is equal to 1 minus 1/4, or 3/4. Okay? I'm going to square root both sides of my equation. Okay? Bring my work up here. And x squared, square rooted, is x. And that is going to be equal to, and thinking back to our exponent rules, we can apply the square root to both the numerator and denominator separately. So I'll have the square root of 3 divided by the square root of 4, which is 2. So the value of x is the square root of 3 over 2. Square root of 3 is a little more than 1.7. So if you think about an approximation for this, it's about 1.7 over 2, which of course is a little bit bigger than 1/2, which is the length of y. So when I come back to my unit circle here, I know the cosine, or the x length, is square root of 3 over 2, and the sine is 1/2. Now, that is, I think, the trickier of the two special right triangles that we have to take a look at. The next one is this angle pi over 4 here. So similarly, the cosine and sine for this angle, the x and y coordinate of that point, are going to correspond to the x distance traveled and the y distance traveled, which will again construct a right triangle. Now what I'm going to do is I'm going to pull this triangle out again, and we're going to prove what the value of cosine, in other words the x length of this triangle, which corresponds to the x coordinate of this point, and the sine, or the y length of this triangle, what those values have to be. Okay, so here is the angle, the right triangle that we've constructed. I just pulled it out of the unit circle, and we know this is a right angle, a 90-degree angle, which is pi over 2 radians. This is pi over 4 radians, and so if you're just thinking about what does this missing angle have to be, consider that every triangle, the interior angles of the triangle, must add up to 180, and as you, I'm sure, are aware, a 180-degree turn is pi radians. So all the interior angles of a triangle have to add up to pi radians, just like they did over here. You can go back and check. And so if I have pi over 2, and I'm actually going to write this out so you can see, I have pi over 2, that's the 90-degree, plus pi over 4. And if we add those two together, you're going to get, if you add these two together, you get 3 pi over 4. And that's almost a full pi, right? In order for this to just be a full pi radians, you'd need this to be 4 pi over 4. So what we need to do is add another pi over 4 to the mix, meaning that this angle here has to be pi over 4. Okay? And the purple side corresponds to cosine, which is the x distance, and the green side, of course, the sine of the angle pi over 4, or the y distance. Alright, and now we have a situation that is going to lend itself a little bit more easily to proof, and here's why. Notice that these two angles are equal. So the angle opposite the x distance and the angle opposite the y distance are the same, which means that the distances have to also be the same. So x and y, they're equal, meaning we can represent them using the same variable because they are the same thing. So let's represent them as the variable a. Okay? So now, in order to find the x distance, the cosine, and the y distance, the sine, we just have to find the value of the variable a. And again here, I have a situation where I can utilize the Pythagorean theorem. A squared plus a squared equals 1 squared. And since that equation will only have one variable that I'm looking for, I can solve for it. A squared plus a squared is 2a squared, and 1 squared is 1. So I have 2a squared is equal to 1. Dividing by 2 on both sides gives me that a squared is equal to 1/2, and then square rooting both sides. Notice that I'm doing a lot of work in kind of one place to save a little bit of room. Will leave me with a is equivalent to the square root of 1, which is 1, over the square root of 2. Okay? Now this looks maybe a little different than the values that you've memorized, and that's because in math there's just a common convention, sort of like common courtesy, of not using a square root or any radical in the denominator. And so the way to get rid of that, and I'll do this work off to the side, is if I have 1 over the square root of 2, and I want to get rid of a square root, let's just multiply it by the square root of 2 over the square root of 2. Because now in the denominator, I'll have square root of 2 times square root of 2, which is just 2. And so in my denominator, I now just have the value 2. And in my numerator, I have the square root of 2. And you can test to see that this is the same as this. Plug it into your calculator and you'll get the same value. Square root of 2 is about 1.4, and so 1.4 over 2, right, a little more than 1/2. And so each of these values, x and y, are going to be equal to the square root of 2 over 2. All right, and so that's the proofs for the special right triangles that we use to construct all of the special angles for a unit circle. One tricky one to note here is finding the reciprocal of root 3 over 2. So you might at first think that's 2 over root 3, square root of 3, and it is, but you always want to write it with a square root not in the denominator. So you can multiply by the square root of 3 over the square root of 3, because that's just 1, and now you have the square root of 3 times square root of 3 in the denominator, which is 3, and in the numerator you have 2 times the square root of 3. So the three trig functions that we've learned, cosine, sine, and tangent, they have, of course, reciprocals. And the reciprocals are known as secant, cosecant, and cotangent. And they're very, very simple. And so we can use the reciprocals as well to describe certain relationships, and we'll graph them and look at them. But just very basically, let's define them. So the cosine, the reciprocal of cosine is secant, the reciprocal of sine is cosecant, and the reciprocal of tangent is cotangent. So we can write out these relationships. And there you have them. The secant of some angle x is 1 divided by the cosine of that angle x. The cosecant is 1 divided by the sine of that angle x, and the cotangent is 1 divided by the tangent, right? They are just the reciprocals. So a reciprocal of something is 1 divided by that something, and that's why we get these three reciprocal functions. Now in practice, these are actually very easy to compute, right? As you did in the last question, finding the reciprocal of fractions just entails switching the role of the numerator and denominator. So the reciprocal of 1/2 is 2 over 1, or 2. The reciprocal of 3/2 is 2 over 3, so on and so forth. So when I'm finding the reciprocal of cosine, for example, I'm just reversing the role of the numerator and denominator. So let's do a quick example. Let's look at the secant of 7 pi over 6. You should try this on your own first. So the cosine of 7 pi over 6 is negative square root of 3 over 2. So the reciprocal of that is going to be negative 2 over square root of 3. Now I never want to have a radical in the denominator, so I'm going to multiply by square root of 3 over square root of 3, and that will give me a new value that is equivalent to the original value, negative 2 times the square root of 3, all divided by 3. And so the secant of 7 pi over 6 is negative 2 root 3 over 3. And you should practice these, maybe come up with, write a couple on your own. I would recommend practicing cotangent a couple times, because you have to find the tangent first and then find the reciprocal of it to find the cotangent. And if you want to, on your unit circle, you might go around and you might at least note to yourself that the relationship that secant is 1 over cosine, that cosecant is 1 over sine, and that cotangent is 1 over tangent, so you never forget that. Okay, now this might have seemed tricky at the beginning, but this is actually a very, very simple relationship that we have really already covered. And that comes from our construction of how the unit circle is made up, right? So for any angle along my unit circle, no matter where I've rotated, the cosine corresponds to the x-coordinate and the sine corresponds to the y-coordinate of that particular point where the terminal side intersects the unit circle. And we know that no matter where the terminal point ends up, we can construct this right triangle where the vertical side is the length of sine, the value of sine, and the horizontal side is the value of cosine. And for any right triangle, we know that the sum of the squares of the two smaller side lengths must equal the square of the hypotenuse. And since our unit circle has a hypotenuse of 1, for any angle that we create, cosine squared plus sine squared will always equal 1 squared, or 1. And so from that comes a relationship, an equation, which is going to be very, very helpful. And I'll explain why in just a second. But let's go ahead and define this more clearly. Okay, so this is what's known as the Pythagorean identity, and what it really is just the Pythagorean theorem applied to the unit circle. And what the Pythagorean theorem says is that if you have a right triangle, you can take the two smaller sides, square them, add them together once you've squared them, and that will equal the hypotenuse squared, right? A squared plus b squared equals c squared. And so here we just have a special situation where our hypotenuse c, regardless of where I end up on the unit circle, the hypotenuse of that right triangle, constructed with the cosine and sine, in other words the x and y coordinate, is going to be 1. And so this allows me to write the equation that the cosine value, the x distance, or this side length, squared, plus the y distance, or this side length, squared, will equal the hypotenuse squared, which is 1. Now notice that I've written this a little bit differently, where I have the squared in between the cosine and the argument, in other words, the angle x, or the value of x. And this is how you write cosine squared. And what this means is that you are multiplying cosine of x times itself. So as I wrote it on the previous slide, this is saying find the cosine of x and square it, meaning that you are going to take cosine of x and multiply it by itself. Okay, that's what that means. And so, for example, the cosine of pi over 6 is root 3 over 2. So if you wanted to apply this to pi over 6, what you would say, and we'll just do a little example down here, is that the cosine of pi over 6 squared plus the sine of pi over 6 squared is equal to 1. And you can check that this works, right? So cosine of pi over 6 is square root of 3 over 2, and then you're squaring it, meaning you're multiplying that by itself. So you have the square root of 3 over 2 squared plus the sine of pi over 6 squared, and the sine of pi over 6 is 1/2, and then you'll square that, and that should equal 1. And if you square 1/2, you're going to get 1/4. And if you square 3, you're going to get, if you square root, let me repeat that. If you square the square root of 3, you get 3. And if you square 2, you get 4. And so when you add these together, you will get 1. Okay? And that will work for any angle that you rotate. And you might be wondering, well, what happens when we have negative values? Well, that's where the squared part comes in, right? When you square a negative value, so for example, I were to go down to 7 pi over 6, if I were to square negative root 3 over 2, when I square a negative, it will become a positive. So even if this were 7 pi over 6, add a little 7 here, now all of a sudden this is negative, and this is negative. When I square them, they become positive, and so it will work, right? No matter where or what value of x I'm working with, what angle I'm talking about. Okay? And this has a couple of nice corollaries. So coming from this, I can solve for cosine by itself. I can also solve for sine by itself. So as a part of this, we have two things, what are called corollaries, or equations that are coming from this one equation. If we subtract sine squared of x on both sides, I get that the cosine squared is equal to 1 minus the sine squared. And similarly, I can solve for sine squared, which is going to be 1 minus cosine. Now, this is going to be very helpful because in some situations we may not know both the sine and cosine. We may not even know the angle. And so we can utilize this equation to help us solve for a missing trigonometric value. And we will kind of put this all together in an example right now. Okay, so here we have a situation where we know the sine of x is 9 over 16, and we know that x is between pi over 2 and pi, and we were trying to figure out what the value of cosine and tangent for this particular value of x is. And so before we dive into finding cosine and tangent, let's just think about what we're told here. So the key piece of information they give us is that the value of this angle x, or we can think of it as an angle, is greater than or equal to pi over 2 and less than or equal to pi. So if you're thinking about a unit circle, where in your unit circle are you going to be? Well, here is pi over 2, and here is pi, and so you're going to be somewhere in the second quadrant. Okay? Now, we can also think about what we're told when we're told that sine of x is 9 over 16. Remember, sine is the value of the y-coordinate of the point that intersects the unit circle at the terminal side. So, if I've rotated somewhere into the second quadrant, somewhere along here there's a point where the y-coordinate is 9/16. And so we can consider, what is 9/16? Well, 9/16, 8/16 would be 1/2. So 9/16 is just a little more than 1/2. And if you think about where in our second quadrant is the sine or the y-coordinate going to be 1/2, that's at 5 pi over 6 radians. So where would I have to move in order for the y-coordinate to be just a little bigger? It'd have to be a little upwards, and so the angle is going to be something a little less than 5 pi over 6. Alright, now last but not least, remember we're trying to find the cosine and the tangent, and we know that our angle is right around there. What do we know about the cosine and the tangent for an angle in the second quadrant? Well, you know that the cosine is going to have to be a negative value, and then the tangent is also the slope of this line is going to be negative. So both the tangent and the cosine are going to be negative, and so that is going to be a really important piece of information to keep in mind when we go about solving for the cosine and the tangent. Alright, now let's come up with a little bit of a plan for how to solve for cosine and tangent. To find the tangent of an angle, we need the cosine and the sine. So let's go ahead and find the cosine first. Now, using the Pythagorean identity, we have an equation where we have sine and cosine involved, and so if we can plug in the value for one, we can solve for the other. And particularly here, if we want to solve for cosine, we can do 1 minus sine squared and find the cosine squared. So let's use that, and cosine squared of x is going to be equal to 1 minus, now sine squared, now sine is 9/16, so we have 9/16 squared. And so cosine squared is going to be equal to 1 minus 9 squared is 81, 16 squared is 256. And that means cosine squared is going to be equal to, and let's subtract this, 1 is 256 over 256. 81 minus 256 is 175, and so I have 175 over 256. And that is the value of cosine squared of x. But we're looking for cosine, not cosine squared. So let me take us to a similar example. Let's say you have x squared is equal to 4. How do you find the value of x? You square root both sides, and that will tell you that x is either plus or minus 2. So moving over here, if we square root both sides, we will have that cosine of x is equal to plus or minus, and now we can take the square root of both the numerator and the denominator. The square root of 175 is about 13.23, so let's use 13.23 as an approximation, and the square root of 256 is 16. Now notice that we have that it's either positive or negative. And this gets back to going into the second quadrant. We know the cosine is going to be negative, so we know the cosine of x in this particular quadrant has to be negative, right? We know there's some other point, in the first quadrant where the cosine has the same value but is positive. And so that's why it was so important for us to remember that this is when x is in between these two values, when we're in the second quadrant. And so we can just get rid of the positive option, because we know it's not going to be the positive version, and we have that the cosine of x is negative 13.23 over 16. And if I were to estimate that, come up with an approximation here, I get that 13.23 divided by 16 is approximately 0.83, negative 0.83. Okay, and this is an important comparison here, Because we want to think about our comparison angle that we had at the very beginning of our work here, and that was 5 pi over 6. So at 5 pi over 6, cosine is negative root 3 over 2. And if you were to compute negative square root of 3 over 2, you would get that that is about negative 0.087. So we can see that the cosine value is a little less than that. And so if I were to mark here 5 pi over 6, and then think about the angle that we're at, which has to be a little above, a little less than 5 pi over 6, notice that the x value of the green mark is going to be a little bit less than the x value of the red mark. And so this angle here should have a cosine, this angle x should have a cosine that is a little bit less than 5 pi over 6. So I can be confident that I found the correct value. Okay, now to find tangent of x, I'm going to take sine of x, 9/16, and divide it by cosine of x, which is negative 0.83, sorry. And when I do that, I will get the tangent. So why don't you compute that and see that it makes sense. So tangent of x, and here we have 9/16 divided by negative 0.83. And I would just go into my calculator here. I know this is going to be a negative value. And it's going to end up being about negative 0.68. Okay? And why does this make sense? Remember that the tangent is the slope of the terminal side. And so if my terminal side is there, then the slope of this line should both be negative and should be, it's a pretty shallow line, right? The slope of the line that is halfway here, or 3 pi over 4, that has a slope of negative 1. And so this line should have a slope that's a little more shallow, and so we should have something less than 1, and sure enough we do. So we're able to find the cosine and the tangent. So the Pythagorean identity is very helpful because, in short, if we know the sine or the cosine, we can find the other value. But notice that we have to decide which quadrant we're in, or whether or not the cosine in this case should have been negative or positive, because when we square root both sides, we aren't able to tell whether we want the positive or negative value. So we have to use the other information that we're given in order to do that. Alright, well that was all for this video. We learned a couple of new skills, and so make sure you go and practice them. You can come up with questions like this on your own, and you could go around and look at your unit circle and maybe even pick some out to just kind of reaffirm your skills with this. And of course there will be more in the assignment.